curve is showing the temperature of the bread dependent, y-axis, as a function of time since the bread was removed from the oven. So that's the black curve. And we're pinpointing the time 4.753 minutes after we pulled the bread out of the oven. Okay, we want to think about, so does this curve of temperature versus time since we took the bread out of the oven, is it a constant rate of change? Is it a constant rate of change?
At certain moments it is.
Okay, he said at certain moments it is. So, yes or no? Is it a constant rate of change?
No.
Why no? So who said no? Yeah. Okay, because it's not linear, right? So it's no because it's not linear, right? So the rate of change is doing what? It's changing, right? The rate of change is changing, and we see that because it's a curved graph. But then he said yes. Why yes is it a constant rate of change?
Because in a moment it is.
Right, exactly. So if you pick any moment, if you pick a small interval, it's essentially constant rate of change for any small interval of time. So overall, the rate of change is non-constant, okay? But what we're talking about here is if we zoom in far enough, if we look at a small enough moment, then we can assume that the rate of change is essentially linear in that small moment of time. Did you talk about this on Friday? This kind of stuff? Okay. So now this is, I've set this up, and those pink arrows are showing at this time, so 4.753 minutes. Those pink arrows are showing a value of dx to the left from 4.753 and to the right from 4.753. And what we want to do is we want to zoom in until we find a moment at which a constant rate of change exists. Okay, so we want to zoom in. And so you can zoom in by, if you hit Shift, I'm hitting Shift right now, and then you can make a box. And that zooms in. So right now I'm showing dx as 2. So dx is going forward from our point in time we're interested in, and dx is going 2 back. Okay, it's going forward and back by 2 minutes. So what moment are we showing here? We're showing a moment from about, what, about 2 minutes to 8 minutes or something like that, right? We're showing from about 2 minutes to 8 minutes. And do we have a small enough moment to have a rate of change at this moment?
No.
Why not? It's still curved, right? It's still curved. So we got to zoom in more. Okay, so I'll come in here, I'll Shift. And maybe I'll zoom in this much. Okay, what's my moment now? My moment now is about 4 minutes to about 5.3 minutes, right? I'm showing from about 4 minutes to 5.3. Remember, a moment is an interval. And right now my moment is about from 4 minutes to about 5.3 minutes. And what about now? Am I showing a constant rate for this moment?
No.
Still a little, so that red line is showing a constant rate, and the black is our actual curve, and it's deviating away from that line, so it's still curved. So I want to zoom in a little bit further. Maybe like this. Yeah, maybe like this. Why isn't it working? What's going on? One more try. Still not. Okay, so getting closer. Yeah, maybe a smaller box. But each time I'm zooming in, so.
Mark,
Yeah.
the red line, it's going off of dx, so when you change the value of dx, it will match.
Right, exactly. But so the instructions in your homework say to get it to be to get it right and then change dx. That's why I'm doing it this way. Okay, so maybe every time you zoom in, you have to change dx. So the instructions, I think, are a little misleading because, yeah, so what's happening is that red line he's right. The red line is still graphing for this very large dx of 2 compared to our thing. So I'm going to start over, and And I think it's better if you change dx as you go. So you have to do this in your homework, so I'm glad we discovered this. So I'm going to zoom out. Okay. So here we're going to start again. So we're going to zoom in. Okay, and then we're going to change dx. So we're showing a moment, again, from like 4 to 6 or something like that. So let's change dx to what? Like 0.2. Instead of 2, let's change dx to 0.2. All right? And so now we can zoom in on that and take a look at, so now my dx is shown by those pink arrows. That's a dx of 0.2. What do we think? Do we have our rate of change at the moment yet? Still deviating a little bit, so we can do better. So let's do, just say 0.1. And now we'll zoom in on that. Okay, now we're making progress here. So what do we think? 0.1? Okay, we can do a little better. We can do a little better. So let's do 0.05. Zoom in on that. Okay. So here we've got our dx of 0.05. And so what's our moment? Our moment is something like, kind of the whole width of the screen I'm showing here is like the moment. So that's like 4.6 to, we could say 4.8, that's fine. $4.7, thank you. 4.7 to 4.8. And dx is 0.05. Now it doesn't have to be half the width, so I'll just do 0.02. And certainly for that 0.02, so now here's the thing about calculating the rate of change. Once you have the moment where you're essentially linear, you can calculate the constant rate of change using 2dx, right? So that's what this program does. This distance here is actually 2dx. Or you can calculate the constant rate of change using a single dx. It just depends which correspondence points you're going to use to do it. But any two correspondence points within this moment are going to give you the constant rate. Okay, so I could use those two correspondence points. This program is using these two correspondence points, or this particular file. The one that's for 1dx less, and the one that's for 1dx more. We could start here. We could use this correspondence point and this correspondence point. It doesn't matter, okay? So there's no, once you have the moment such that you have a constant rate, any two correspondence points based on dx or 2dx will calculate this constant rate of change. Okay, so you're gonna see it different ways, and I don't want you to think there is a certain way to get the constant rate. If you have the moment that has a constant rate, then any two correspondence points based on dx or 2dx will generate that constant rate. So taking a look at the file here, notice what? It's based on 2d. It's calculating m based on 2dx. You see that? So it's using this correspondence point and this correspondence point and finding dy over dx. And it finds that to be negative 27.0625, and that is degrees Fahrenheit per minute. Okay, so what does that number mean? What does that number mean? Negative 27.0625 degrees Fahrenheit per minute. I want you to tell the person next to you, we want to apply what we've learned. Don't go back to who you were before this course started. You've learned something new about what this number means. That's what I'm asking you. What does the number negative 27.0625 degrees per Fahrenheit per minute mean? Go. Okay, here we go. Let's regroup. Where's Kindil, Kanwar? Kindil. Yes. The slope in the moment. Okay? So that would be like a visual representation. Slope is a visual representation, but that number, what does that number mean? Where's Preston? Preston, what does that number, negative 27.0625 mean? What's that? The rate of change. Okay, yes, it's the rate of change. What does that number mean? Where is David Diaz? Oh, okay, we're making some progress now. You said the change in temperature is equal to negative 27.0625 times the change in time. So I'll use capital T and little t to be temperature and time. Okay, which said in a different way. Can we say that in a different way? Where's Lily? Lily Wayne. Yeah. Right. So given any change in time, the change in temperature is negative 27.0625 times the change in time. But now there's something new to this. She got it. What else is new to this that we didn't have before? Yeah, Sam.
Over the interval of 4.7 to 4.8.
We have to have a dt, a little dt, that's in the moments. What happens if dt gets too big? It's not true anymore. Why? Because this outside of the moment, we get a different rate of change. So now our dt has to be small. So for a small change within the moment, so for a small change of t within the moment, we have this relationship exist. But as soon as that dt, the d little t, gets outside of the moment, that won't hold anymore because our rate of change is changing. You see? So we got that same relationship, but it only holds in this moment for that constant rate of change. Super important. Okay. Given any change of time, given any small change in time within the moment, the change in temperature is negative 27 times that change in time. Okay. Any questions on this review and kind of some of your homework? So in your homework it says keep zooming in and then change D. I think you should keep changing the D to be within your moments as you're zooming in each time. So tweak the homework instructions a little bit. Does it make sense? Yeah. This is okay. Yeah, this is okay. It would be so this is good because it'd be such a small Fahrenheit per second that this is okay. But it wouldn't be wrong to do that. But this is all right in that case. Other questions? Okay. So now let's look at. So for this bread function, are there any moments where we don't have rate of change in a moment? What do you think? Would there be any moments where we don't have a constant rate of change at a moment? Is there any place where we could zoom in and we couldn't get it to be linear? No, it's a nice smooth curve, right? This is a really friendly, nice smooth curve. Any moment, any time we could pick, we could pick a small enough moment to see that the rate of change is changing essentially constant, at a constant rate. Okay? What about this one? Do we have rate of change in a moment at every one in this one? No. Okay, you are looking up here. So what happens? No matter how much I zoom in, and why? And so why is that? What's the problem with that? No matter how much I zoom in, I'm not going to get a constant rate of change in that moment. It's going to be some positive rate to the left, and then suddenly this negative rate. You see? That will always happen no matter how much I zoom in. All ones and all twos. So I've zoomed in so much that GC can't even give me enough precision anymore. And the point is that at that point, so what about right here? Is there a rate of change of the moment right there? Yeah, it's that positive rate, right? So I could zoom in and get that, do a moment right around there. That would be essentially, let's see if I can do it here. I tried to get like this. There. All right, so this is a really, really, really small fraction to the left of that cusp. We've got rate of change in a moment. So it's only at that one point. It's only at that one point where, if that's the center of the moment that we want, we can't get a constant rate at that cusp point. It's called a cusp. A corner point in a displayed graph is called a cusp, and that's a cusp. All right, so let's look at this one. So this is called the Blancmange function. I like to say it, Blancmange. Okay, so we're going to look at this what is it? Did you read about this? This is at 1.215. So at 1.215, we're going to zoom in here and take a look at what's happening. So is it a positive rate of change or a negative rate of change at 1.125? So I can change the red for this particular program I've created. I can change it. It looks negative to me, right? Look negative like that? So let's zoom in and make sure that that's true. Okay, so now, it's more like 0. Something like that. So is it positive or negative here? Positive? So I'm zooming in here, and I'm looking for my constant rate. I keep zooming in. What's going on here? Oh, it's negative. Look at that. I'll zoom in again. We'll get this thing to flatten out, right?
No.
Oh, it's positive again. So what's going on here? I keep zooming in, but it keeps showing up like this piece of cauliflower, right? It keeps showing all these cusp points. And so this is a very special function that's a continuous function. It exists for all values of x, and it's continuous. But it doesn't have a rate of change at any moment. At every moment is a cusp. Every moment is a corner point. That's pretty cool to think about. Like you kind of can't wrap your head around it. No matter how much I zoom in on this thing, it keeps being wrinkly or bumpy, or there's a corner. So it's like there's a corner everywhere. There's a corner everywhere. So we don't want it. So like that nice smooth temperature for the bread, we don't want to take that for granted. It's really nice to have a rate of change at every moment. Not all functions. It's possible to have a function that has like a corner point at every moment, and you can't get a constant rate of change. Okay. So here I'm beyond the precision of the program here. I've zoomed way, way in, and it's still showing lots and lots of corner points. Why? Because there's corner points everywhere. Every single x value is a corner point. It's hard to wrap your head around it. Okay, what are we doing next? Okay, so you guys talked about a fast man last time, right? What? 3 Olympics in a row, he's won 3 gold medals, right? So let's continue that discussion. All right, so here I'm showing, let's go ahead and show it for something you don't have. Yeah, 3 is great. Okay, so this is the function. T is the elapsed time since Usain started his race. This is for not this past Olympics, but I think it was, when was it? 08?
It was the one in Beijing. Yes.
No, he didn't break the world record in the Olympics. So he beat the world. He had the world record of 9.58 seconds at some other running track meet. It wasn't the Olympics. So I think it was. I don't know where it was, but this is based on that, where he ran the fastest 100 meters that anyone's ever run in the history of anything. Okay, 9.58 seconds, and that's what this graph is based on. It's his distance is dependent. Y-axis, the dependent variable is distance for time in seconds since he started running, and this is a polynomial version of that run that he made. So let's make that bigger. Okay, so T is the time elapsed since the start of the race. F of T is his distance from the start in meters. And we want to talk about, let's just start with talking about at 3 seconds since he started the race. At 3 seconds since he started the race. So first of all, did he run at a constant rate? Did he run at a constant rate? Because, we know he didn't because it's curved, and it would be absolutely impossible to, at 0 seconds, instantly start running at a constant rate. Everything that moves in the world, in the universe, has to accelerate. It can't just instantly be at a different speed. So when speeds change, they change gradually. It may change fast gradually, but things need to accelerate from rest if they're going to gain speed. Okay, so they can't just immediately gain speed, and so then we know there is his distance time graph is not a constant rate of change, but we can also say it is constant rate of change if what? We look at a moment, right? We look at a moment. So now we're going to look at the moment of c equals 3. So we'll come here and I'm going to zoom in. Z equals 3. And as I zoom in, I've created something else here that you couldn't see before. So now I'm going to zoom in again. And so how about this for a moment? Does this look like a small enough time interval that gives us a rate of change at a moment? Does it? I think so. And so what is this moment? We got the moment, like say 2.98 to 3.04. So 2.98 to, so this is about 3.04. So our moment is 2.98 to 3.04. And within that moment, I'm showing a dx here. So now I'm just going to use a single dx. In your homework problems, you're using 2 dx's within the moment. Here we're just going to use a single dx. But again, if we have constant rate of change, any two correspondence points we can use to calculate that constant rate of change. So we've got this initial point. And then we have this, and so there's a dx there, but I'm not showing you what it is. I'm just showing it visually, but we don't know what its value is. So can we represent the coordinates of these 2 points exactly? Okay, so we know, the only thing we know is that the x-coordinate at this first correspondence point is 3. So can we exactly represent the y-coordinate and the x and y-coordinate of this second point? This is practice, so we're not to the sheet yet. This is practice. So can you do that? So give it a shot. Talk if you need to. Can you represent the coordinates of this point, given that it's at 3 and that our change in our differential is, we're saying dx, but you don't know its value? Can you write the coordinates of this point, these points? Okay, where's Zara Hadzik? Did I say it right? Zara? How'd you do? So what about that first correspondence point? What'd you say for its exact coordinates? She wants 3 and f of 3. Very good. And can you keep going there? So then what'd you put for the x and y coordinates of the second point? Okay, so that would be just estimating from what you're looking. Can we write that exactly? Can we write that exactly? The way you wrote f of 3, right? You symbolized it. So how could you symbolize this value of x exactly? He wants to join in. Yeah. 3 plus dx, right? 3 plus dx. Three plus dy. Okay. But there's you want to do f of 3 plus dx. Okay, again, it's function. So everything's coming together at once here. Got to know function notation. Constant rate of change. All right, so then your sheet. Hold on a sec. Okay, let me have your attention. Some days we might go a minute or two over, and then I'll try to give you the days back on other days, okay? So I didn't really give you the cue to pack up, so just remember that for the future. I know that it's 10:30, so just want to talk, this sheet is now going to be, in addition to what's already been assigned for written homework, will be written homework for Wednesday. And so the first thing you're going to do is, you're going to fill in these 3 boxes right here, which is very similar to what we just did. But now you also have to, based on those 2 correspondence points, write out what that rate of change will be. Okay, this is all symbolic. Okay, this is all representation, no values. Okay, then you're going to look on Blackboard. There's going to be a file similar to the one I was showing, a GC file, where you're going to go through and you're going to do what I did, and you're going to set C to these different values. Then you're going to zoom in, and you're going to calculate. You're going to calculate values now for each one of these based on changing C and zooming in to get rate of change in a moment for each one. And then the rest, follow the instructions carefully. And that it'll be this sheet in addition to what I already assigned over the weekend for written homework on Wednesday.